So we are going to have a chill day. At the end of class, we had just started talking about survivorship curves. So remember, we had just finished up talking about the importance of birth and death rates when we are looking at overall population growth. And that while they can vary between individuals, when we're trying to understand overall populations, what we really want to pay attention to is how the overall species copes with birth and death. And this is what survivorship curves let us do. And so we're really looking at, for a given generation, which is what cohort means. There we go. Really looking at like a generation. So born within a given group. Okay? How many survive? Okay. So of a cohort, right, birth group. Okay, how many are born? Okay, and survive to old age. And when we say old age, we really mean through at least one reproductive success. Showing up on the screen. Okay. Okay, so for some organisms, like us, this may mean the potential to reproduce many times, okay? But for something like a salmon or a lamprey, okay, this may just mean once. Okay, but you have to do it at least the once. So that's what we mean by old age. Okay. So as we think about that process, okay, we can sort of lump organisms into three groups. And as we'll find, only two of these groups are particularly common. The middle one is fundamentally pretty rare. My brain's back on my shoulders, so. With me so far, definitionally? Let's look at some examples then. If we look at the blue curve, this is what we're sort of most accustomed to. When you have organisms that follow the blue curve, I'm drawing. What you expect is that at birth, okay, we see, right, remember our y-axis here is, my crabs has covered it, so I'm going to rewrite it. Number that survive. Okay. So up at the top here we have high survivor. Okay. So for your blue curve, okay, what you find is you have high survivorship with your offspring. Now this comes as a trade-off, right? Because if you're going to have high survivorship with your offspring, this also tends to mean that you have more investment in your offspring, right? You're going to have very few of them. So you're going to imagine this like humans, right? We have 1 to 2 at a given time. We give birth to 1 baby at a time. Even if you have more than 1 child in a family, okay, they're not giving birth to more than 1 at a time usually. As a result, the offspring mortality rates are very, very low. Okay? Even if you have a family with large numbers, right, you're caring, you're investing in those, and by very large numbers, we usually mean 3, maybe 5. Anything more than that is more uncommon, right? John and Kate +8, those numbers that's uncommon. Anything bigger than that is certainly more uncommon. Not unheard of, but uncommon. So families have few offspring, and you spend a lot of investment on that offspring. Okay? 18 years of my life I cared for my child. Right? You house them, you feed them, you provide them education, and not just academic, right? Teach them how to care for themselves so they don't ideally fall flat on their face the second they step out of their house. And be functioning adults. How to cook, how to clean, how to, right, be human. Okay. There are several other mammals that do this. Think like other primates. They will care for 1 or 2 offspring for an extended period of time. High survivorship. Now the trade-off, of course, is if we follow this curve, is that we get higher death rates. Naturally, you got to die sometime, right? In the older age. When the body is eventually and naturally going to start to break down. Okay, so that's where the larger portion of our population is. So a higher proportion of our population then is going to pass away in that older age group. After everyone has already had a chance to reproduce at least once. Get at least one go around the merry-go-round, right? Does that make sense? Everybody kind of see how we work through that side? Okay, now let's hop all the way over to group 3. Group 3, we see the exact opposite occurring. Okay, and this is probably one of the more common or most common reproductive strategies. So we follow this graphic. We see we have very low survivorship. Okay, this thing is like jumping off a cliff, right? If we started at 1,000 individuals, right, not very many of them are making it past that first age class. Okay. Now again, this comes with a trade-off. Okay, we have very little survivorship, okay, but we have lots of offspring. Pretty much no investment. Okay. We're going to picture this as something like crabs, many fishes. Okay, so lady crab, okay, drops her spawning larva into the water. Has lots of videos of this. She just rears up, shakes them off. Good luck, little ones. I'll see you in 3 years. Okay, it's really cool to watch. Okay, if you've not seen videos of this, so there's just thousands upon thousands of little larval crabs being released into the tide. Okay, so there's no parental investment besides whatever nutrients they were given while they were inside mob. They on their own. Okay, so we can imagine statistically the chance of an individual larval crab surviving that. Right? So they are food, delicious, delicious food for literally anything bigger than they are. And they're so small that they are going to be at the whims of the waves. Okay? So being able to not get smashed to death, not end up in the pit of despair, okay? Being able to find their own food, the odds are stacked extraordinarily against our little crab bebes. Okay? Very Lord Farquaad, right? Some of you may die, but that's a risk Mommy is more than willing to take. Because she has not then had to put years and years of effort into it. Next year, she'll just pop out another 1,000. Okay? Because also statistically, you drop 1,000 babies into the water, okay? 1 or 2 or 5 are probably going to make it. Okay? The odds are in the favor of that. And that's what we see here, is as we get towards these bigger age classes, a few are going to make it, they'll be a little bit bigger. And a few more will die. And then a few will make it, and they'll be a little bit bigger. And the bigger you get, okay, the more and more likely you are to survive. Until you're an adult crab. And adult crabs are pretty tough, right? You still can die. Predators can still pick you off. Okay, so as we get down here, a little bit. Okay, you get the heavy-duty part of the population. Okay, our adult crabs that are not sensitive to death, okay, because they're tough and meaty. They're big enough that they can control where they swim. They're big enough to find their own food. A very small proportion of predators are capable of taking them on. Okay, so until they reach the point where they're likely to kick off on their own, okay, they can tough it out. You just gotta get there, little larval babies. So most organisms fall into one of these two groups. Not all, but most. Does group 1 versus 3 make sense? We see the benefits and trade-offs, quite frankly, of each, both from the baby standpoint and from the parents. All right, so the adults over here have low death. Okay, so let's take a hot second. I'm going to clear off everything I've got on here just because there's a lot on here. Let's take a second to look at group 2. So group 2 is a little uncommon, okay, but not unheard of. So most of the time we find group 2 in birds. Right? So in group 2 we find that pretty much throughout our entire life you have an equal opportunity of death, which is a little weird. Okay. So we find these in like small to mid-sized birds. Anything from like a songbird to a smaller stork. Okay. And so if we think about something like a songbird, okay, they tend to have 3 to 5 babies at once, right? So it's not a small amount, right? That's more than 1 or 2 at a time, but it's definitely not 1,000. Now, it's definitely not in the middle, but you can't really cut in the middle between a small and 1,000 without definitely reaching closer to 1,000. So we're going to do 3 to 5 babies. Okay. The life of the nest is tough. Okay. If the babies don't all hatch at the same time, they can roll each other out of the nest. Brutal. Right, so our likelihood at this age would be quick death. Okay. If resources are scarce and mommy laid too many eggs, we see this particularly with things like loons and ducks. Okay. Mommy may choose babies to off. Okay, so we see this with like ducks and loons will like drown babies. You don't have as many to feed, which increases the likelihood of some of your babies surviving. But, I mean, we're like culling the herd, which is kind of like, okay. So we have that same sort of likelihood of just like being guillotined randomly. And then as we think about being in adulthood, so we've passed that age, if we think like halfway here being reproduction, you're just a small freaking bird. Okay, so the likelihood of getting picked off by a predator, about half the predators on the planet are bigger than you. Okay. And they're pretty sensitive. Right? So a lot of these birds are migratory. Okay, so migration picks a lot of them off. Okay, and they're also sensitive to things like habitat fragmentation, et cetera, where a lot of these other organisms are not as sensitive to that in the old age. Okay, so many birds, for example, are very sensitive, and so they're just as likely in their old age to be kicked off as they were when they were small. It's still not a bad strategy, right? Because at no point in their life were they super highly likely to die. Where for both of us, right, in the 1 and 3 group, there's a point in your time, in your lifespan where you know you're very likely to kick the bucket. But the trade-off here is there's also no point in their life where they are very significantly likely to be safe or likely to survive higher survivorship. So it's an unusual strategy. I really can't think of too many organisms beyond these like songbird types that utilize it. So it is certainly the most rare strategy. I'm very nervous and okay, any questions about our survivorship curves? Does this feel good and much better now? Less chaotic. Okay, now keep in mind that while we've generalized and said, well, humans fall under, right, the 1s, and crabs are 3s, and songbirds are 2s. This is generally true, okay? But populations of species, for example, can vary. Okay? So while all humans tend to be 1s, okay, the way the curve itself looks is going to vary between populations, right, depending on access to resources, access to healthcare, who took their vaccines. Okay. We also find that males and females have different curves. This is not necessarily as true in humans, although, for example, we know males and females tend to have different longevity. We do find that this is very true for other organisms. So if we follow, for example, the 3s, okay, oftentimes males have significantly shorter longevity than females. Males tend to have a ride or die. They invest a lot of energy in getting lots of matings in. Females tend to live a little bit longer. All of their fecundity comes out of having many, many years of many offspring. So where a female may have a long curve, males may shorten quite quickly, right, and have a blunt tip on it. Okay. And certainly if we consider cohorts, remember this term means generations, and so if you have a year that has very good resources, good environmental conditions, or we had just the right amount of rain this year, then they're going to have a nice curve. Okay, they had good resources growing up, so they're going to be healthier. If you had a cohort that had a rough youth year in particular, that even carries over into adulthood no matter how long they live. So if they had droughts, for example, okay, so resources were scarce, it's often difficult to get that youth body mass back in adulthood. And that goes for adults and I'll let it just kind of happen. In the animal kingdom and the human kingdom, right? Large losses in body mass are often very difficult to maintain and retain in a healthy fashion after loss. Okay, so even though we would expect the general shape of these curves to be similar, the actual curves themselves may differ due to a lot of these biotic and abiotic variables, right? Like sex, location of the population, or like these abiotic conditions. Okay, this still feel good? Nope, one of the other pieces that play a role here is called age structure. And this is really easy to see in human populations, but it matters in both. So we've talked a lot about age class, and we saw that in our growth curves, and this is the same piece. So age structure is a piece of age class. So age classes, and humans just tend to say age, but this really has to do with age grouping. Okay, so what part of our population is in the youth category, right? Less than working age, okay? Working age, above working age, retirement, and then very elderly, needs care. That tends to be how we think about it from an economic standpoint. And that tells us a lot about how a given state functions, for example, economically. Or different countries function economically. Do you have enough of a working class population to sustain your non-working population? Is your youth population large enough that it's going to, predictably in the future, right, be able to continue to sustain your population as it grows elderly? Okay. When we think about this from an ecology standpoint, we think about it very similarly, but of course we're interested in pre-breeding, breeding, and post-breeding. Okay. So the way that you can start to graph these things are what we see here. Okay, so at the bottom you have the population size, Okay, so how large or how many individuals are in each group. And then in this, we have how our age classes are broken down. So this is an economic one I have up, for example, on here, although it's not, as we see, broken down as well as I think most people would do. This should really be 2 groups probably. You can see the shape of these are really important. Okay. So if we think about this, for example, if I were to look at this from an ecology standpoint, okay, and I look at Nigeria, I can say that this is the population that has positive population growth, right? As I look at this box, and I know we're talking about humans, but okay, humans are animals too. Okay. My green box is our breeding population. Organisms that are of the age at which they can have children or offspring. Okay. My blue box is the youth or juvenile box. Okay. So how many offspring are currently subsisting in the population? So how much is that population going to be growing in the future? So we see that our breeding population is quite large, and better when you're looking at a population. Okay? Our blue population, our population of future growth, is quite substantial. It's very wide. Okay? When I look at the top box here, now I want to be clear, I know we're talking about humans, this doesn't mean that you're not of any value past the age of 45, right? But you tend not to have children past this age. So we're just going to call this post-breeding is all. So we think about this as a breeding population. Okay, this is quite small. Okay, it's narrow. Okay. And all that really matters here is that it's more narrow than the breeding population. Okay, so we're seeing a growing trend. Okay, individuals that are breeding, adding to the population, are larger than those from the previous or older generation. If we think about this from a human standpoint, this also means those in the working class, okay, are a larger group than those in the retirement class. All right, now let's look at the negative growth box. Okay. If we look at Japan, okay, we see an opposing story. Okay. My breeding and my juvenile boxes are quite narrow. In particular, we see that the offspring or the juvenile box is in fact the most narrow of all of the categories. And so what this tells me as an ecologist is that the future generation for this population is very small. Okay, so I should not expect to see the next generation of this population to be very big. In fact, I should see it shrinking, which is of concern. Okay. Of course, part of that is because our breeding population, our green population, is also not very large. Particularly in the years that are most prominent, right? For humans, we would expect these to the 20s and 30s. be most prominent in producing offspring, and those are the smallest boxes. And lastly, and also concerningly, it's one of those good bad things when you think about things from a human perspective. We see that the post-breeding segment is the largest. Both in that, in this case, it's containing some of the widest sections, and we've actually added some sections, meaning that individuals are living longer, which is not bad, but it's bad when you're thinking about a growing population. And so you have individuals lasting or subsisting in a very long time in this population, but you do not have individuals supporting that from an economic standpoint, okay, or from a population standpoint. Okay, so this is a population you would imagine get very top-heavy. Okay. So economically, right, you would have the retirement age get pushed way more and way more and way more out because there's no one coming in to do the work for the economy. And you would imagine shrinkage within itself, right? So the country itself would want to think of what can I do to convince people either to move here or more children. We've seen countries do this in the past as well. And for what it's worth, this stuff is not that old. It's 2017. Okay. Anybody see, does everybody understand how that we look at this sort of data and the kinds of information that we get out of it? Now, of course, when we look at other animals that we don't have economic information from it too. I think that's usually what we're used to taking out of this. So the key when we're looking at this is make sure that you both understand, okay, what is the right now, okay, which is the breeding and post-breeding, what's happening in the moment, and the juvenile is what can I predict in the future. And both of those things are really important for understanding what is going on with a population. Okay, should there be concern? It just looks like I'm coloring it something. Shiny? Yes, that is exactly what we just did. All right. So the way we can start looking at this, okay, changing those graphs into actual predictions, is using what are called life tables. Life tables are a way that we can take information of how many individuals are breeding this year, how many people are going to be in the post-breeding, okay, survive into that next year, okay, how many offspring are they going to produce. Okay, we can take all of that information in a very tangible way. We call those life tables. Okay. So these are really valuable when we're looking at a population because it allows us to actively and very tangibly predict future population. And remember, I said we often do this in a way to decide should we be concerned. We call that population health. So life tables contain a lot of information. And so we're going to go through practicing using them very slowly. Okay, but certainly we're going to go through things like birth and death rates. Which ultimately become implied in what we call survival rates. You see death rates are in survival rates. So quite literally, what proportion of the individuals from a certain age class are likely to survive to next year? Okay, so if I look at age class 0, I would read that and say that 30% of individuals that were just born will make it to see age 1. Everybody see how I read that? I can do that for the next year. Look at age 1. Okay, I can read that and say 80% of the individuals that are age 1 will survive the age 2. I'm bigger, I'm more likely to survive. What's happening at age 2? If I read the next row, how would I read the next row? 0% survive, all right? Age 2 is our kappa. Okay. So for whatever species, it's hypothetical, I've made this up, okay? You cannot make it to age 3. Okay? It's like a salmon. You breed age 3, okay, and then you crawl into the bottom of the river and you die. Happy. Okay, so nobody makes it to age 3. Everybody see that? So we see what those survivorship, so we're going to use the survivorship rates a lot when we do our calculations. Okay. We can also see the death rates in what's called the survivorship number, although we're not actually going to use them in our calculations. But they can give us valuable information. It's not my favorite number. You'll see this come up a lot. Okay, so I can read that and say that at age 0, everybody's alive, 100%, right? You would imagine that. I've been born. I haven't died yet. More importantly, let's look at age 1. At age 1, 30% of the population has survived. So it's pretty much just the inverse of what we just said, right? We just said that 30% of the population died to get here. So this is 30% of the population then, right? It's pretty much just the inverse, more or less, of our survival rates. But we're not going to use these much for calculations. We'll use them a little bit in lab, so I wanted to introduce it. The other thing we're going to use a lot here, though, are our birth rates, which are shown in fecundity. Fecundity is a term that's used a lot that basically says reproductive capability. Okay, so for every individual that you are, how many offspring are you capable of producing? And so, at age 0, I have just been born. I am too little, and I cannot produce any offspring. Makes sense. Most organisms can't produce right away. But at age 1, I've gotten big enough, still pretty small, okay, but I can produce some offspring. So for each one individual at age 1, I can produce 2 offspring. Okay, see how I'm reading that? What about for my 2-year-olds? How many offspring can they have? 4. Why can I have more offspring at age 2 than I could at age 1? Humans aren't like that, right? I'm bigger, okay? A lot of organisms are like that, okay? So as a fish, right, if I happen to live more than 1 year, okay, I'm probably bigger next year than I was this year. So I can hold more babies. Okay, so sometimes fecundity goes up. What if it goes down? Why might fecundity go down? It didn't here, but it might, right? Humans, in fact, goes down. You get some kind of cell breakdown. It just reduces your likelihood of being able to reproduce successfully. Okay, less eggs are released. Okay, less chance of successful sperm-egg bonding. Whatever the case is. Okay, so you'll see, as these numbers change, fecundity also tends to change. Any questions about the information that we can find on a life table? Okay, I'm going to go ahead and stop there today. On Monday, we're going to start with some population statistics, and we're going to work through actually being able to predict year-to-year population size using this very life table setup.